All right, so my name is Alina. I'm a graduate student at University of Massachusetts in Amherst, and I'll be talking about some of the experiments we've done with quantum vortices in Spinor Bose-Einstein condensates. So just to start, this is just all the people who have participated in these experiments. As you can see, it was a collaboration between many different people and institutions, but the bulk of the work has been, the experimental work was carried out at Amherst College under Professor David Hall. So a brief introduction to vortices. I think they hardly need an introduction. So first of all, they're a naturally occurring phenomenon, which we're all familiar with, such as in water. And then we have, in the superfluid context, we have, in scalar superfluids, we're all familiar with, I'm sure, vortices in superfluid helium, as well as Bose-Einstein condensates, as well as other systems. And so in a scalar system, the vortices are always quantized with a phase winding of 2 pi. Now, when we add internal degrees of freedom in certain phases of superfluid helium, as well as in Spinor Bose-Einstein condensates, things get more interesting. So, so that's what this talk is going to be focused on, is vortices in these Spinor Bose-Einstein condensates that have internal degrees of freedom, which makes things more interesting and complicated. So in the context of BECs, so first to start with scalar BECs, we have our wave function, or as I will call it in this talk, the order parameter, which has a scalar density and your gauge or superfluid phase. So the mass flow around a vortex is simply given as so, and it depends on the gradient of phase. Now, in the case of a Spinor Bose-Einstein condensate, we have an additional term, which is a vector order parameter. So this zeta term, which makes things more interesting, because the superfluid flow around a vortex, or even just any kind of flow around a texture, depends on not only this phase, superfluid phase phi, but it also depends on your kind of spinor orientation. So your geometric orientation of the order parameter interacts with the superfluid phase and makes things more interesting. Now, I will just take a minute to move this view so it's not in my way. Okay. So in this talk, I'll be talking about our experiments, which we've done in the spin 1 Bose-Einstein condensate. So this Spinor order parameter zeta is a 3-dimensional order parameter. So we are dealing with a hyperfine spin F1, and we can choose a basis to represent this vector, which will have 3 spinor components, which are the Zeeman sublevels, which we're probably familiar with from basic quantum mechanics. So we'll always observe the spin textures that we observe are always observed divided among the -1, 0, and +1 Zeeman sublevels. Now, additionally, the internal degree of freedom also introduces the possibility for magnetic phases, which I know also exist in superfluid helium. But in a spin 1 Bose-Einstein condensate, there are 2 possible magnetic phases for the ground state. And so we have what we call magnetic phase and the polar phase. So on the left, you have your vector representation of these phases, and on the right is just a spherical, this is a spherical harmonic representation, just for, as a visual aid. Now, in the case of the ferromagnetic order parameter, we have kind of a donut shape. I mean, you can think of p orbitals, like your orbitals around your kind of electron orbitals around in an atom. So it's the same principle here. So again, this is just a visual representation. So the details don't matter so much as what we get from this representation. And as you can see, in the ferromagnetic phase, we have an orientation of this donut, like if you imagine an axis going through the donut, and we have a phase, the superfluid scalar phase, which is represented in color. So you also have, you have your orientation of the donut and then a rotation of your donut. So that's your kind of, those are your degrees of freedom of this order parameter. Now in the polar phase, it's slightly more restricted. You have a kind of a principal axis, and you have a discrete symmetry of the phase. So we'll be looking into the details of this a little later on in the talk. So, okay, just to give a sense of what's up ahead, I first will describe some of the basics of our experiment, since we are an experimental group. And then I will talk about, in two parts, just going over two experiments which are published separately in two papers. The first one deals with vortices in the ferromagnetic phase, and both singular and non-singular vortices in the ferromagnetic phase. And the second part will be about vortices in the polar phase. So a little bit about the experiment. So we have a double Mott magneto-optical trap system. So we load about 2.5 times 10 to the 5 rubidium-87 atoms, which we can prepare in any state, but in this experiment that I'm describing, we start with a ferromagnetic phase. And the way we do our magic is it's made possible with 4 sets of coils, magnetic coils, which generate a quadrupole field, along with an offset field, which moves the quadrupole field in any desired direction. Now, additionally, what's important to note is that after we make our condensate, we load it into a crossed beam dipole optical trap. And this is important because when your BEC is optically, you have a spin degree of freedom which is not frozen, unlike the case of a magnetic trap. So in a magnetic trap, your BEC spin degree of freedom is frozen, and if you want to work with spinor BECs, you have to have all optical trapping. Additionally, our condensates are roughly spherical, so it's a 3-dimensional system, it's actually it's roughly a cylindrically shaped trap. And when we do the actual topological experiments, we hold the BEC in the optical trap, and then the magnetic coils are used to create the magnetic field, which then imprints the topological texture. And just kind of a blow up of what that we imagine it looks like. So the main thing is this quadrupole shape field. The black arrows here are the magnetic field. And with 3 pairs of Helmholtz coils, we're able to move the field 0, which is the red dot in this case. We're able to move the quadrupole field 0 in any direction, which allows us to create all kinds of topological excitations in the condensate. Alrighty, and last but not least, for the experiment, the way we observe the topological textures is we once we turn off the optical trap, condensate falls and expands, and at the very end, we apply a magnetic field gradient, which separates the 3 Zeeman sublevels, and we take a picture of the 3 components, and we do this simultaneously from what we call a top view and side view, which I'll be referring to later. So yeah, that's the gist of the experimental part. So moving right along to the first results. So this work was published in Nature Communications fairly recently, and this work focuses on creating singular SO3 vortices from a non-singular spin texture. So in order to understand how this works, I will first give a little more theoretical background. So we have our ferromagnetic order parameter, which is an SO3, call it an SO3 order parameter because it's essentially described by a triad. So this is very convenient and lucky because we can actually visualize what's going on with the order parameter pretty intuitively. So the group of SO3 rotations, which are just your ordinary 3-dimensional rotations, can be mapped onto a sphere. And for those who are a little bit familiar with homotopy theory, the way we determine whether a topological excitation exists or not, or the way we characterize the topological excitation, we have to look at the order parameter space, which is the space of all possible configurations of our order parameter. So in this case, the solid sphere, all points inside the sphere describe possible rotations of the triad. Now, Vortex is essentially characterized by whether a loop in that's mapped from the Bose-Einstein condensate to the order parameter space, whether this loop is contractible down to 0 or not. So in the case of ferromagnetic phase, there are 2 types of vortices that are possible, and it's actually a pretty unique system because all that matters is whether the winding number is even or odd. So any even winding number will contract down to 0, whereas an odd winding number is an odd winding number gives you a true topological excitation, which is a vortex, which is a non-contractible loop, right? So at the top here, we have actually going around the sphere, we actually rotate the triad by an angle of 4 pi. So this type of loop is contractible through the, if you could just contract it down to 0, and essentially what that means is that this is not a topological excitation so much as just a spin texture, and it's not a true topological excitation. Whereas in down below here we have 2 representations of what we call singular vortex, meaning that it's not contractible and you can't just do away with it. So once you create it, it will not, you can't continuously deform it down to the ground state. And this is because in this representation on the sphere, points on the surface of the sphere, antipodal points are actually identical. They're identified. So this spherical representation is a little bit redundant, right? So the way SO3 maps onto the sphere, antipodal points are identified and are actually the same. So this half arc here represents going around singular vortex, and it is not contractible because those points, the antipodal points, will always have to remain antipodal, and you can't contract them. And so this is a true topological excitation. However, if you add one vortex and another vortex, you will get something that is contractible to 0. So, so the fun part is that SO3 vortices have this property where no matter of regardless of your winding direction, 1 + 1 will always add to 0. So this is kind of unique and different from, say, the scalar BEC case. Okay, so the way we create these textures is, so we start on the left here. So the blue blob is the BEC in the ferromagnetic phase, and we bring down our quadrupole field. And initially, all your ferromagnetic spin vectors are roughly aligned. And as we bring down this quadrupole texture, this process is nearly adiabatic. So, well, essentially adiabatic. So the spin vectors will follow the field. So on the right-hand side here, we show how we just ramp through the condensate. And if we start with a state of +1, we'll end up with -1. However, I say nearly adiabatically because we actually go a little bit faster, such that some atoms in the field near the field 0 is very, very weak. So some of the atoms near the center will actually not follow so well. So we end up with some residual, kind of in the middle, we end up with atoms that have not completely flipped to the -1 state. However, the whole thing, the whole BEC is still ferromagnetic. And we end up with a texture which is represented here. There's kind of no very super clear way to represent this kind of texture. It's just, it's essentially a winding of 4 pi of the triad around the middle. So you can, for example, follow the green arrow around the outer edge. And if you do so, you will eventually count your 4 pi winding. Okay, so that is all well and good. And that is a non-singular spin texture in the sense that there is no singularity in the center, and this texture is completely deformable down to the ground state. And this is, on the top here is a simulation, and on the bottom is the experimental result of what the non-singular texture looks like. So these are the 3 components that we've separated in our imaging, and this is a view from the top. We've ramped from the top to the bottom, so we can see the simulation shows us a little more clearly, but in the experiment also we see basically something that when you put it together, there's no singularity in the center. So, so the interesting part is what happens after when we wait a little bit, because there's an instability-driven decay of the system. We speculate due to the very sharp bending that results in the middle. So for example, here you have a -1 orientation, spin orientation, and right in next to it, you have something that's +1. So this is a very energetic, this is a very sharp bending, and it's energetically unfavorable. So in our experiment, we just wait a few milliseconds, and we actually produce something that looks like this. And I will actually go to this slide because it's a little more clear. So what happens is the non-singular texture decays into 2 singular vortices of 2 pi winding each. And unlike the original textures, these are actually true topological excitations. Again, on the bottom, we have this experimental result, and on the top is the simulation. So the residual atoms that did not convert all the way down to -1. So there's a spin exchange process actually, which converts some of the ferromagnetic phase to the polar phase. So this is what we see in the middle here. These 0 atoms are actually evidence for a polar phase, and they fill the cores of the ferromagnetic vortices. And again, this is just having to do with the system decaying into an energetically favorable state. And on this slide, for example, this is another image with this now including a side view on the bottom here, and the top view on the top. One of the vortices in this case, so we always get 2 vortices that appear from a non-singular texture, but one will run away sometimes. So this is just an example where only one SO3 vortex remains, and from the side you can see clearly the filled core of the vortex going all the way through. And on the right hand side, then we have the colorized version, where, yeah, again, you can see that the polar phase fills the vortex, the ferromagnetic vortex exactly. And there are some interesting physics that might be happening at the boundary between these 2 phases. So that's an additional point of interest. All right, so just to conclude this part, this is again just a theoretical visualization of the singular vortex with a polar phase filling the center. So the order parameter here is represented by the polar phase, and going around the edge now, you can see that the green arrow rotates by 2 pi instead of the 4 pi that we had originally in our non-singular texture. So, okay, so that is the first part of our work, and the second part is actually something that we can do once we generate these SO3 vortices. So this part kind of builds on previous work, and we actually use a magnetic phase exchange to interchange the phases. So we change ferromagnetic to polar and polar to ferromagnetic. And from our ferromagnetic SO3 vortices, we get polar vortices with ferromagnetic cores. So again, just a little more detail about the polar order parameter. So to describe the polar order parameter, it is useful to map the spinor into the real vector, which we call the director, which is just, it just points in some direction in space. And the polar phase is in the BEC, it's distinguished by the fact that there's a discrete spin gauge symmetry. So, right, so in the polar phase, if we take the polar order parameter and reverse the direction of the director and add a pi phase to our superfluid phase, then the order parameter is unchanged. So this actually reduces the space, and then it makes half quantum vortices possible. So this is just a graphical illustration of how that works. So if we have something that's just an ordinary, what we think of an ordinary vortex, which is a rotation of 2 pi about some center, we can deform this ordinary vortex into two half quantum vortices. And the reason this works is exactly due to this discrete spin gauge symmetry of the polar phase, because when these two representations of the order parameter meet, using this symmetry property, we can actually see that this point is continuous. So a pi phase winding in, so a 180-degree rotation of the director together with a pi phase winding of the phase, which will happen, the phase flip here is necessary to guarantee the continuity of the order parameter. That generates your half quantum vortex. So the circulation is pi instead of 2 pi. And lots of work has already been done on half quantum vortices, and this is just some examples in sodium BECs and then superfluid helium. And I might be missing other superfluid helium people, and I'm sorry if I am. Right, so in our work, actually, we basically have come close to observing these half quantum vortices in rubidium condensates. So the principal part of the experiment revolves around this magnetic phase exchange. So in the last part of the talk, I explained how we make these SO3 vortices in the ferromagnetic phase. And here, all we do is we take those vortices and we apply a series of microwave pulses, which actually Robbie coupled these, the hyperfine F1 and F2 levels. So at the top here on the right-hand side, and there's a color triangle representation. So we start with ferromagnetic condensate in the +1 state with 0 polar cores. So going from the 1-0 state, we drive the transition. So we drive both the M0 and the M+1 states up to 2-0, and then we drive. We basically exchange with a third pulse. We exchange the two phases. So we drive what was originally in the +1 state into the 0 state, and vice versa. The 0 state gets driven into +1. Yep. So yeah, and just to demonstrate, so this demonstrates here on the bottom the resulting topological texture. So we end up with a polar condensate with ferromagnetic cores. Okay. Now, yep, just another kind of clearer image, so more complete picture. As we can see, there are no. We start with something that has no atoms in the -1 component, and so after our 3 Rabi pulses, we end up with something that completely just flips the two phases. Now, these are just singular vortices in the polar phase. So to make things more interesting, we actually drive another instability, and this time we do it through a radio frequency pulse. So in fact, in this configuration, our d vectors of the polar order parameter are aligned with the magnetic field. So there's a constant magnetic field that the condensate sits in, and this is actually a stable configuration. Whereas when we here, as I show here, when we make the d vector perpendicular to the field, this is an unstable configuration. So So this radio frequency pulse couples our 1,0 state to the plus and minus 1 states. So this kind of condensate, which is in the polar phase, so it will, well, essentially, so we just rotate the d vector by 90 degrees or pi over 2, and this and what it effectively does is just distributes the zeros into plus and an equal part of plus and minus 1. So there's no magnetization. It's still a polar condensate. It's just this is the configuration where the field is perpendicular to the director. Now, right. So then, when we evolve this kind of system, we observe something which hints at the presence of, or the decay of, these two vortices, the singular vortices, into two pairs of half quantum vortices. So again, we are looking at from the top at the 3 Spinor components here, and the right-hand panels here show the magnetization, which is just subtracting the plus and minus 1 components, which gives you your net magnetization of the system. And for reasons I don't have time to go into right now, in the polar phase, the hallmark of a half quantum vortex is what you would see is 2 holes filled with plus and minus 1. So that's in the polar phase. This is the hallmark of observing 2 half quantum vortices. Now we start at 0 milliseconds and we wait for 50 milliseconds here at the end. The time markings are a little small, but we're going in increments of 10 milliseconds. And what we observe is, as time goes on, we see this in the magnetization images, we see bright spots and dark spots. So the dark spot corresponds to magnetization facing one way, and the bright spot corresponds to the magnetization facing another way. However, we are still stuck with some residual polar atoms in the very center, so in the cores. So after our pi over 2 rotation, actually the polar atoms also rotate, or excuse me, sorry, the ferromagnetic atoms, so the ferromagnetic core, the atoms in the ferromagnetic phase rotate also. And when we project like we normally do and observe the texture, right, the perpendicular orientation of the ferromagnetic vector shows up in the M0 component. So this is what we're seeing here. So these residual 0 atoms kind of prevent the guarantee of the presence of half quantum vortices. But as time goes on, so if we wait for like 50 milliseconds, we see that we do not observe any more 0 atoms. And the circles here are just the same. We just take them from, they're in the same location as the holes in the plus minus 1, which is where we would look for the 0 atoms. So we do not see any here. So this result strongly suggests that we observe the presence of half quantum vortices. So yeah, so this is kind of in summary, the 2 projects that we've done, sort of if we look at them all at a glance, we start with something in the ferromagnetic phase with something that is just a rotation of your spin vector, a 4 pi rotation. And it's non-singular texture, which is deformable to the ground state, continuously deformable. And then through instability, we observe the decay of the non-singular texture into two singular SO3 vortices. And then after we drive this magnetic phase exchange, we end up with two polar vortices, which after the rotation of the vector by the RF pulse gives us 4 half quantum vortices, or strongly suggests the presence of 4 half quantum vortices. So that is all I have for today. So I welcome any questions.
Thank you very much. This is very interesting. Does anybody in the audience have any questions? Please raise your hand. I'm not seeing any immediate ones, so I'm going to ask one myself. Now there's Albert, please.
Sorry?
Albert, I think.
Yes, thanks. I wanted to ask about in this last part, is the total density modified by the presence of the half quantized vortices that you find with respect to an initial configuration which you don't excite anything?
Sorry, you were talking about the second part, part 2?
Yes. Yeah, I'm asking if the total density is modified, not the magnetization, which is of course in which you of course see these bright spots and dark spots, but the total density.
I mean, I'm not sure I understand. So the overall density does decrease just due to trap losses. But do you mean the density of the entire condensate, or?
I mean, of course, you have a total density, which I understand it should be the sum of the densities of spin -1, 0, and 1, right?
Mm-hmm.
My question is if you observe something in the total density when you have half quantized vortices there. I mean, do you see, I don't know, a small modification of the, I mean, I understand that this can depend on the interaction, because there is, of course, interaction dependent.
Oh, so when compared, so it say for the same amount of evolution when compared to not having the vortices in the condensate?
Exactly.
Oh, offhand, I'm not sure. I'm not sure if we've done a direct comparison. So, I think the quick answer would be I'm not sure. So are you asking about like losses that would be driven by the presence?
No, not about the losses. I mean, ignoring losses, because there are several papers that say that when you have well, I mean, these papers I know are in 2-component systems, but I don't think they should be different in 3-component systems. Although I'm not sure about the role of the polar phase here, but when you put a half quantized vortex or something like that, there is a small depletion of the total density in that position due to the compressibility of the system, or the fact that you have a also the compressibility is finite. I mean, it's not fully magnetic, but I always wondered if this is the same case in Spinor systems when you have more than 2 components, which is this ideal case in which you can ignore one of them. This is something I don't know, to be honest, and I wanted to ask you if you observe something like this.
I mean, the only thing I would say is maybe somewhat close is we do observe that I didn't mention this in the first part of the talk, that when the SO3 vortices are filled, we see that they're filled with the polar atoms. We actually see that this has an effect on the size of the vortex core due to them being filled. But yeah, with regard to the half quantum vortices, I really can't say, and I'm not sure if we can Yeah, if we can't, because it's also evolved such a long time, 50 milliseconds is actually quite a long time. So there's just a lot of variability also.
Hmm.
Yeah.
Okay. Okay, thanks.
All right. I was going to ask one thing. Might be a stupid question, but I think you said that that the half-quantum vortices are not stable in the configuration where this D vector is perpendicular with B vector, the field. Could you explain what the reason is?
Oh, the instability right. So I'd said that so when originally in our configuration, the field is aligned with the D vector. So this is a stable configuration. I am not exactly sure actually what drives the instability in the perpendicular case.
Because
this is like
out of just as a curiosity, in helium-3 there is a similar instability. I mean, although the system is different in many ways, but indeed, if you rotate the magnetic field, the half-quantum vortices are either stable energetically or not. And this is because they are either connected by solitons in the spin space or not.
okay.
And so then I was kind of curious whether this is actually what happens here as well, or is there some other reason?
So actually, there are two. So we call them. I don't know if it's the same in superfluid helium. We call them easy axis polar and easy plane polar. So depending on whether your director is aligned or perpendicular with the field, and I mean it has to. So they are actually two phase. So they are categorized as two phases, two different phases, even though they have the same symmetry properties. But as far as magnetic phases, they are different. So, I mean, that's kind of the depth of my theoretical understanding.
That's all right.
Yeah. So I guess it's disadvantageous for the. I mean, the vortices that they have holes, so it's more favored for them not to overlap, but to slide off of one another. And I just think, yeah, I kind of think of this as some, energy considerations that theorists deal with. And being an experimentalist, unfortunately, I do not know exactly.
All right, that's fine. Yeah, and I'm sorry, I'm going to torture you with another theory question, which you may leave unanswered if you like. But so in the first part, you were talking about the core of the non-singular vortex in the ferromagnetic phase being filled with, I think it was the polar phase, but some other phase anyway. Is this just kind of an observation based on the components which you can measure, or is there some like simple, hand-waving reason why it should be the case?
Yeah, so something like this, right? SO3 vortex filled with the polar phase, which is correct. So is your question, how do we know it's a polar phase and not something else? Or
well, as I understand, you measure the different components here as we see, yeah. So that's kind of how you know it. But there's probably some reason. Okay, you can simulate it. So the simulation, I suppose, will agree with this. So this means that there is a reason why it is that phase there. But is there some simple understanding why you should expect that?
Yeah, so I mean, in general, like in a BEC, so a vortex is a singular vortex, means you will have singularity in the center, so you can't have any atoms there, at least none in the ferromagnetic phase. So if we have a vortex in the ferromagnetic, in the center you have your singularity, so no atoms are allowed at the center, and the size then is determined by your BEC healing length. It's the healing length is actually a sharp, so this would cause a very sharp bending which is just energetically very costly. So in general, in the BEC, having a hole, like a true density hole, is very energetically costly. So that's one thing. In the simulation results do confirm this instability, which leads to basically spin exchange between the -1s and the +1, which generate your zero. So that's how you get polar phase. That's how you make polar phase, basically. So in our experiment, it is a little nuanced because we have to ramp through the condensate at a particular rate. If you make it very, very adiabatic, you're not going to have enough of these zero atoms and those atoms hanging around, which you need basically for your spin exchange to make polar phase. Now, the reason the condensate wants to make a polar phase is just because having a filled core is way more energetically, it's cheaper. It's just a lot cheaper than having like a real density hole. Yeah, so does that kind of answer your?
Yeah, I think so. Someone's writing in the chat. All right. I'm not seeing. Okay, now there's Dima. Dima, please.
I have a stupid question as well. So in the superfluid scalar 3A in half quantum vortices, the prediction is that they host Majorana fermions as excitations bound to the vortex core. So is there any similar predictions about your sort of system, the BEC system? Some interesting excitations in the core of the vortex.
I offhand would, yeah, unfortunately, I know nothing about the presence of Majorana fermions in BECs. It's kind of very much outside my area.
Oh, that's fine. Yeah.
Yeah.
Well, maybe I can jump in. So obviously, in a Bose system, you will not have fermions, but there might be some other sort of excitations in the core.
Yeah. So I mean, the core. The core structure is obviously of interest in our case because, right, so the core can do many things, including splitting into this half quantum vortex configuration. But in our system, everything kind of tends towards a lower energy state. So everything we observe, we don't really drive a lot of these, these processes sort of tend to be dissipation driven. So going toward a lower energy state. So I don't know if that helps at all. I'm not sure about like categorizing excitations within the cores. So.
Yeah, because well, this system is of course you can visualize it a lot easier than superfluid theorem 3, so it would be interesting to look at some sort of excitation. But yeah, thanks a lot.
Or I mean, if there are suggestions as to how to drive these excitations, we're welcome to hear it. So.
Are there any other questions? Well, as there doesn't seem to be any other questions, I'm gonna thank the speaker for giving a very interesting presentation and the audience for a nice discussion afterwards. And then the next webinar will be in 2 weeks' time. We will post information on the website and send reminders by email a bit closer to that time. And that's all by my side. So yeah, thanks again.
Thank you.